take a look at an oscillating pendulum. So here we'll have m be the mass of the pendulum, and L is going to be the length of the rigid rod to which the pendulum is attached, and theta will be the position in terms of angular displacement. And so then the principle of angular momentum states that the derivative of the angular position is equal to the moment of force applied to the pendulum. And so the angular momentum of the pendulum about the origin, labeled capital O in the diagram, is ml squared times the second derivative of theta. And then we have damping. So this is the moment of resistance. Moment of resistance sounds like something from an adventure movie or something. So that's L times C d theta dt. And then there's also the component due to gravity. And so gravity is going to be mgl sine theta. So that's the horizontal component pushing this way due to gravity. And so then putting this all together as an equation, we have ml squared theta double prime is going to be equal to minus cl theta prime, minus because it's damping, so it's counter to the direction of motion. And then we've got the restorative force minus mgl sine theta. So again, that's a restorative force pushing you back towards equilibrium, so that's also with a minus sign. And then dividing through by ml squared and moving the negative terms over to the left, this becomes theta double prime plus c over ml theta prime plus g over L. Whoops, sorry, that's a sine theta. G over L. Sine theta being equal to 0. And so we can rewrite this as theta double prime plus gamma theta prime plus omega squared sine theta for gamma equal to this c over ml, and omega equal to the square root of g over L. And now we can convert this to a system. So by taking x to be theta and y to be theta prime in the usual way, then this leads us to x prime is going to be equal to y, and y prime is going to be equal to minus omega squared sine theta, sine x, minus gamma y. So there we have it as a system. And now to look at the critical points. Of this system. So this is when the xy vector is equal to 0. Well, then that's going to be either when y is equal to 0 from the first equation there, or when minus omega squared sine x minus gamma y is equal to 0. And that second one there, so if y is equal to 0, then we're just going to be looking at when sine x is equal to 0. And so then that's going to be when x is some integer multiple of pi. Okay, so now we can see what happens, or take a look at what happens. So if we take 0, 0, or more generally, an even multiple of pi and 0, then this guy is going to be stable. So for x sufficiently close to 0 and y sufficiently close to 0, we'll have phi t tending to x naught. And so it's not only stable, but it's also asymptotically stable. Meanwhile, if we look at the critical points of the form 2n plus 1 pi 0, so you can just think about pi 0 if you like. Well, this is the situation when the pendulum is standing straight up. Right, so it's like if here's the hinge, then we have the rod going straight up and the pendulum balanced like right on top. And so this is unstable, because if we start just slightly, anywhere slightly changed from this, so if x is not exactly equal to pi, so in other words, if we tilt it just a teeny tiny bit, then things are going to move, and it's not going to tend to pi 0, it's going to tend to 0, 0. And similarly, if we start with y not equal to 0, so in other words, if we stand it straight up, but we start it with a little bit of momentum, we give it a little bit of a push, then again, it's going to swing down to 0, 0. So so this is showing us that the stability condition fails. And so in particular, it fails if we take epsilon to be anything less than pi. So if you take it to be equal to pi, then things are still good. But remember, the condition says it has to hold for any positive epsilon. So as soon as you start looking for tolerances and you say, hey, I want it to stay within, pi over 2 of the starting position, well, then that's not going to work out for this critical point.